Hi, in this video we're going to continue with curve sketching, and so we're going to move on to this next example. So without using a graphing device, sketch the graph of this function. So by now this is the third video, so hopefully you're getting a hang of what the steps are. So first is find the domain. In here I can see right away that we have a radical, a square root. So then we want to make sure that the stuff inside the radical is not negative. Or that is, yeah, not negative. So let's find a domain. So that means we want the inside. So we want x plus 2 to be greater than or equal to 0, which means that we want x to be greater than or equal to negative 2. So our domain then is the interval from negative 2 bracket, including negative 2, all the way to infinity. So that becomes our domain. And the next thing is find x-intercepts and y-intercepts. So to find the x-intercepts, you set y equal to 0 and solve. So when you set y equal to 0, you have 0 equals x cubed times the square root of x plus 2. So that's a times. That means either x cubed is 0, which tells us that x is 0, or this is 0, which tells us that x is minus 2. So those are our two x-intercepts. What about y-intercepts? Y-intercepts are we set x equal to 0. So you'll have y equals 0 cubed times the square root of 0 plus 2. So you just get 0. So 0, 0 seems to be a very common x and y intercept. It's not always the case. Sometimes you have other y-intercepts. I'm not sure why I haven't done those problems, but I want to kind of encompass different types of problems. They just also happen that the x and y-intercepts are 0, 0. All right, so we have our domain, x and y-intercepts. The next thing is identify any asymptotes. We don't have any derivatives, any denominators, so no vertical asymptotes. So I'm going to say no vertical asymptotes. What about horizontal asymptotes? For horizontal asymptotes, we take the limit as x goes to infinity of the function. So x cubed over or times the square root of x plus 2, which as x goes to infinity, you have the form infinity times infinity, which is just infinity. And we can't go to negative infinity because that's not in our domain. Our domain starts when x equals negative 2. So from negative 2 to infinity. So taking the limit as x goes to negative infinity doesn't make sense because it's not in the domain. So no vertical asymptotes, no horizontal asymptotes, no slanted asymptotes. You only have slanted asymptotes when you have a rational function, and if the degree of the numerator is larger than the degree of the denominator. So you will have a slant asymptote for something like, say f of x was something like x cubed plus 1 over x minus 2. X squared minus 2. So this will give you a slant asymptote, and because the degree of the numerator is larger than the degree of the denominator. So, but in this case we don't have any slant asymptotes. It is not a rational function. So let's go to graphing. So in this case there's not really much to plot, right? We only have our x and y intercepts in our domain, and we know that this grows without bound. As x goes to infinity, there are no horizontal asymptotes. So we could try to see what the graph will look like already, but all I'm able to plot really is that I have my x and y intercept here and that the graph grows without bound. So that's really all I know. But when you have vertical asymptotes, horizontal asymptotes, it's nice to kind of go along and plot those as you go. So now the derivative. So let's find the derivative of our function. So we know that f of x is x cubed times the square root of x plus 2. Because I'm going to take the derivative, I'm going to write it like that. So f prime is product rule. I have to use the product rule, right? Because I have x cubed times that quantity. So product rule says the derivative of the first times the second left alone times now, or plus the first left alone times the derivative of the second. By chain rule, just times 1 there, and simplify as much as you can. So I'm going to rewrite this as the square root of x plus 2. And so I'm going to have here, now that has a negative exponent, so this is going to be x cubed over the 1/2, so 2, and then the square root of x plus 2. Ideally, I want to set this equal to 0, so and solve for x, but let's get a common denominator first. So I'm going to put that over 1 so that I can see what my common denominator is going to be. So I just really need that 2 square root of x plus 2. So multiply top and bottom by that quantity. So multiply top and bottom by that. So we're going to have f prime of x equals 2 times 3x squared will become 6x squared, and the square root of x plus 2 times itself. The square root cancels over, and now they're going to have the same denominator. Now that they have the same denominator, I can add them. So I'm going to have f prime of x is equal to same denominator. So now I can combine the numerators. So as I combine the numerators, I'm going to distribute as I go to save some steps. So I'm going to have 6x cubed plus 12x squared, and then plus this x cubed, which gives me then 7x to the third plus 12x squared over that denominator. Factor out the x squared on the numerator, and we'll have just 7x plus 12 over 2 root x plus 2. And now we can set it equal to 0 to find our critical numbers. So my critical numbers are going to be, what are they going to be? Set it equal to 0. So the derivative is 0 when the numerator is 0. So f prime of x is 0 when x squared times 7x plus 12 is 0, which means when x is 0 or when x is negative 12 sevenths. And f prime is undefined when the denominator is 0, which this just means when x is negative 2. And so now let's see about the increasing and decreasing. So let's put our critical numbers on a number line and then find test points. So our critical numbers are negative 2, negative 12 sevenths. So where's negative 12 sevenths in relation to negative 2? Well, it has to be, well, it doesn't have to be before it. So let's see. 7 sevenths is 1, right? So this is then negative 1 and 5 sevenths. So not quite negative 2. Negative 14 sevenths will be negative 2. So then negative 12 sevenths is somewhere over here, not drawn to scale, and then 0. And so we're testing the first derivative. And this is undefined, and this is 0 and 0. So where we have zeros, that's where we have the chance of having local max, local min, or saddle. Undefined, we're not going to have anything there for the in terms of local max or min. And we're trying to see what the function is doing. So we have, let's pick our test points, and I'm just going to rewrite our derivative just to make sure we have it fresh. So it's x squared times 7x plus 12 over 2 square root of x plus 2. So let's pick some test points. How many intervals do I have to test? Really just 3. Notice that this, I don't have to pick a test point there because this part is not in the domain. So this is why we're finding the domain as the first step. That way when we have critical numbers and we go to test intervals, we don't get caught in a place where we're like, why isn't this working? Like if I was trying to plug in -3 here, I'll be like, this is not giving me anything. I'm getting undefined, and that's because, well, this interval is not in the domain of the function. So we're just looking at the ones in here. So let's pick, ooh, this one is kind of hard. So -2, I know -2 is, I can write it as -14 sevenths, right? That gives me -2. So you can pick your test point to be -13 sevenths. I know it's not very pretty to plug it in like that, but, and you can change it to a decimal and then plug it in and see. So, and again, we're looking, we don't necessarily care about the value, but we do care about the sign. Is it positive or negative? So this is going to be, when you square it, you're going to get positive, and then -13 sevenths times 7. That turned out kind of nice, right? So 7 times -13 sevenths, the 7's cancel, so it's just -13 plus 12, which is negative, over, this is going to be positive. Because we are restricting the domain so that that is a positive number, so the bottom is always positive. So I'm going to have a negative. So that means that the derivative is negative, tells us the function is decreasing. So now pick a test point between -12 sevenths and 0. So this one is nicer. We can pick x equals -1. So when x is -1, that's always positive. 7 times -1, -7, plus 12 is positive, and the bottom is always positive. So this gives me positive. So in this interval, the derivative is positive, which means that the function is increasing. And then for the next one, pick something else like x equals 1, and notice that everything is positive. So here the derivative is also positive, and so that means the function increases. So what do we have at 0? Looks like a saddle, right? Because it's increasing, the derivative there is 0, but then it keeps increasing, so this is a saddle. So we have looks like a local min there, and then we have a saddle here, which, back to before, I have talked about our intercepts. Notice that our x-intercept here is 0, and it comes from this term x cubed. So as we cross it, we're going to look like the cubic function there. So the cubic function looks like a saddle when it crosses 0. So that's what we're going to look like. So let's see, can we graph it with what we have? The domain, it starts at -2, it decreases, and then it increases, and it does a saddle as it continues to increase. So if I put my -2 here, let me change the color. All right, so we know that it decreases, and then to -12 sevenths we have a local min, and it will be a good idea to find what the y value is. So to save time, I'm not going to do that work, but essentially plug in your -12 sevenths and find what that local min is. So we have a local min at -12 sevenths and f of -12 sevenths. So whatever this y value is, that's how far down this is going to dip. So you're going to go down, you're going to get your local min, and then, so the function is decreasing, and then we're going to increase, and as we cross there, we're going to have that saddle portion of the graph. So something like that. So it starts at -2, it decreases, reaches the local min, it increases, gets to that saddle, and continues to increase without bound. So that's what we found, because we had no horizontal asymptotes. This part is not in the domain of the function, so this is what our function looks like. So the last thing will be, well, we should check the concavity. I'm pretty sure this is what it looks like, just because I know that as we cross here, it has to create that saddle. So then it's going to be concave down, likely from -2 to somewhere around here. You're going to have a point of inflection right before 0, and then is going to switch to, so it's concave up, and then it's going to switch to concave down, and then at some point over here you're going to have another inflection point where it switches to concave up. So I encourage you to do the second derivative for this and double check the concavity there. And so you should get 2 inflection points, well, and then -2, but that's just going to be undefined because it just comes from the part of the domain where the function is undefined.